Okay, that's Assalamualaikum. Good morning. Can you hear my voice clearly, guys?
Yes, sir.
Okay, good. Okay, as you know, the situation here is not getting any better. Maybe you are aware that we have one positive case in our own faculty here. There is one staff has a positive COVID-19, so all of the FTK staff must work from home since Friday last week until today. We are supposed to enter the faculty going tomorrow, but I guess since the announcement from PM yesterday, I guess we all of us have to work from home for the next 2 weeks. Okay. This is our last chapter, second slide of the last chapter. So maybe next week I will just wrap up and summarize of all the chapters and discuss on your final exam. Okay. So I assume that you have gone through the video that I have uploaded last week. So I'm not going to discuss that one. But you have any questions, problem, just let me know. Okay. So the last chapter here is on light, reflection, and refraction. Okay. So this one and last week chapter is definitely is going to come for your final exam. Okay. So at least you do all the exercise that provided in the textbooks. Okay, this is the unit of the chapter. Okay, first one. Dray model of light. Light very often travels in straight line. We represent light using rays which are straight line emanating from object. This is an illustration, but is very useful for geometric optics. Okay, I want to make emphasize. Okay, this one. Reflection. If we have a plane mirror, straight mirror, plane mirror, okay. So the law of reflection state that the angle of reflection, okay, let me write here. The angle of reflection R, reflection, okay, this one. The angle of reflection that the ray makes with the normal to a surface equal the angle of incidence, the incoming angle, this one. Okay, don't forget that this is on a plane mirror. This is a plane mirror. Plane mirror. Okay, plane mirror. Okay, yeah. So next one. Okay. What about if the mirror is rough? It's not plain. If you see here, the mirror is a rough mirror, rough surface. When light reflects from a rough surface, the law of reflection still holds, still the same. Okay? But the angle of incidence varies. This is called diffuse reflection. Yeah. So it depends on the mirror then. The surface, is it plain or rough? But for both, the law of reflection, which is reflection angle equal to incident angle, is still the same. Okay? With diffuse reflection, your eye sees reflected light at all angles. With specular reflection, specular means plane surface from a mirror, your eye must be in the correct position. Note here, this is diffuse reflection, means the plane is a rough surface. So wherever you are watching from your eyes, right, you can still see the reflection because it reflects at all angle. Okay, but with specular reflection, plane mirror, your eye must be in the correct position. Must be in here. If your eye is in here, you see in here, you will not see the reflected light. Okay, that is the difference between diffuse reflection, which is reflect from a rough surface, and specular reflection from a plane surface. Okay. 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 Questions. Reflection from flat mirror, plane mirror. Two flat mirrors are perpendicular, meaning has 90-degree difference to each other. Incoming beam of light makes an angle of 15 degree. Angle of 15 degree. This one. With the first mirror as shown. So this is the first mirror. This is the second mirror. What angle will the outgoing beam make with the second mirror? This one. This one, huh? Top 5. Okay. If this is 15, so this one will be, because this one is 19, right? So this one must be 75, right? 75. Okay, so according to the reflection law, theta 1 equal to theta 2 equal to 75, right? So this one must be 15 degree, correct? This one 15, this one 19. So this one must be, because this is triangle, 180 minus 90 minus 15. 15.
85.
70. Are you sure it's 85? 180 minus 90 minus 15 equal to 75. Right. It's not 85, 75. Okay. 75. This one 75. That makes theta 3, yeah, equal to theta 4 equal to 15. Right? I hope you can follow this one. Okay. So theta 4 plus 5 equal to 90, right? Equal to 90. This one. Let me draw. Yeah. Because this is perpendicular, right? 90. Okay. The 5 is 90 minus 15 equal to 75 degree. Okay. So the outgoing beam make with second mirror equal to 75 degree. Anyone confused? No, huh? Easy. Eh? Okay, we proceed to the next one. So in the case of a flat mirror, okay, what you see when you look into a plane mirror is an image which appears to be behind the mirror. Okay, so formation of a virtual image by a plane mirror. Exactly the same. The image will be equal to the object. The distance will be equal. It's just the object which will be appear behind the mirror. Okay, this is for the plane mirror. So this is what they call virtual image. As the light does not go through it, the distance of the image from the mirror equal to the distance of the object from the mirror. Okay. Yeah. So we'll go through the. Okay, this one. Okay, just now it's all about plane mirror. But now it's non-plane, spherical mirror. Okay, spherical mirror. There are two types. First one is convex. Second one is concave. Convex mirror and concave mirror. Okay, you can see here the reflection law still holds. It's still applied in here. Okay, so don't forget the shape, huh? Because perhaps it will trick you in the question later on. between the convex and concave mirror. Okay, rays coming from faraway objects are effectively parallel. These rays strike the mirror and they are essentially parallel. Okay, I will go to. Okay. Parallel rays striking a spherical mirror do not all converge at exactly the same place if the curvature of the mirror is large. This is called spherical aberration. Okay. This is what it means by the sentences. If you see here, the light here, all the light, right? They don't just go to converge to one point here. This one goes here, this one goes here, and that one goes here. It doesn't focus to one point. It goes to different point. Okay, this is what they call spherical aberration. Okay, do not all converge at exactly the same place because the curvature of the mirror is large. You know the curvature? Huh? Curvature of mirror is large. This is the curvature. Okay. Okay, we'll discuss in the next slide. Okay, this one. If the curvature is small, the focus is much more precise. The focal point is where the rays converge. Okay. Okay, in this case, can you compare just now, right? This is the curvature compared to the previous one. This is the R here, radius of the curvature. So if you know radius, huh? If I enlarge this curvature here, this is the curvature. If I make it to a circle, okay. So will be the radius. This is the center. This radius then, right? R or this one. Doesn't matter. This one. Radius. So R is radius. This is R from this one. R. Okay. So if the curvature is small, the focus much more precise. The focal point is where the ray converges. So all the ray will go to the same exactly point, which is this one, F. Okay? Focal point. They call it focal point. Okay. Focal point equal to radius of curvature divided by 2. Okay. Spherical aberration can be avoided by washing parabolic reflector. Okay. Example. If you have Astro TV, right? Astro TV in your home, they must have installed antenna at the rooftop usually. That one will be parabolic. The shape is parabolic. Okay. So if you see the antenna, they have a reflector at the end of the antenna there in the middle. They have a reflector. For that one, the function is to avoid spherical aberration. So all the signal coming from the satellite of the Astro TV, Malaysian satellite, will focus right in one point, right in the middle. Okay, this is what they call parabolic reflector. Okay, this is just illustration. Okay, first one, ray 1 goes out from O here, this one, parallel to the axis is this one, parallel to the axis, and reflects through F, focal point, reflects to F. Okay, okay. Ray 2 goes through focal point and then reflects back parallel to the axis. Reflects back parallel to the axis. The third law, R3 is chosen perpendicular to the mirror. This one, perpendicular to the mirror. Perpendicular. Perpendicular means this one has 90-degree difference with the ray coming. Okay. So must reflect back on itself and go through C. So must reflect back because perpendicular 90-degree. So reflect back here. Must both go through C. Okay. There is the simple law of a ray that using a spherical concave mirror. Okay, this one. Okay, this one. There's a formula here. dO is the distance of the object. dO distance of the object. Okay. DI distance of the image. Okay. F is focal point. Focal point. Okay. Let's see example. Okay. M is magnification. So whether the image is getting big, getting larger, or getting smaller. Okay. HI is the height of the image. HO is the height of the object. DI distance of the image. DO distance of the object. Negative sign indicates that the image is inverted. Inverted, huh? What is inverted means? The image is upside down. Okay. The object is between the center of the curvature and the focal point, and its image is larger, inverted, and real. Okay. Let's see example. Okay, this one. Image in concave mirror, 1.5 centimeter high diamond ring is placed 20 centimeters from concave mirror with radius of curvature 30 centimeters. Determine the position of the image and its size. So the formula given is 1 over dO plus 1 over di equal to 1 over F. Question is position of the image. That means image 1 over di equal to 1 over di equal to 1 over F minus 1 over dO. Okay, 1 over this one is what? 1 over 5 centimeter high. This one is HO, height of the object. This one, 20 centimeters from concave mirror. Okay, this one is DO, right? Radius of culvert, okay, 30 centimeters. This one is radius 30 centimeters. Okay. Remember just now the formula? Focal point equal to radius over 2. So, focal point equal to 15, right? So using this one over 15 minus DO is 20. So this one is around 1/60. Yeah. 20 minus 15, 20 times 15 over, this one is 4. So 1/60. So the I is 60 centimeters. Position of image 60 centimeters. Okay, that's A. And then its size of the image. Size of the image is HI. But first we must find the magnification. Magnification just now equal to minus DI over DO. Right. DI is okay 60. 60 over DO is 20. Minus. So minus 3 magnification. So the head is 3 times larger of the object. Okay. So M also HI over HO. HI is okay. The question HO is 1.5 equal to 3. Right. Minus 3. Minus 3. So HI 3 times 1.5 minus 4.5 centimeters. Okay. So the image is minus 0.5 centimeters. Minus means inverted, larger, and real. Yeah. Okay, questions. If the object in this figure is placed where the image is, where will the new image be? If we put HO here, if the object of this figure, this one, in here, right, where will be the new image be? That's the question. So since the equation and physical setup are symmetric between the image and the object, so the new image will be where the old object was. So the new image will be in here, right? Okay, let's see this one. Okay. If an object is outside the center of curvature of the concave mirror, its image will be inverted, smaller, and real. Okay. You can see a clear inverted image of your face when you are beyond C. Yeah. You are here. You are here. This one is bigger than C. Outside the center of the curvature. So this is outside. Okay. So image will be inverted. This is the image. Smaller and real. Because this is beyond C. Beyond 2F, 2 times focal point. Okay. That's not in the question. It's larger, right, by 1.5. Because the object is within the C. But okay, we'll discuss this one in the next week. Okay, now convex mirror. Just now it's concave, this one is convex. Best example of convex mirror is the mirror in the rear view mirror in the car, in every car. Okay. So the image is always virtual, upright, and smaller. Upright. In convex is inverted, right? Yeah, in concave is inverted, larger and real. In convex, it's upright, smaller, and virtual. Okay. Okay, let's see this one. External rear view car mirror is convex with radius of curvature of 16 meters. Determine location of the image and its magnification of an object 10 meters away from the mirror. So the ray diagram for a convex mirror, okay, convex mirror has, we still use the same formula, which is 1 over the O plus 1 over di equal to 1 over F, right? So the question is di. So 1 over di equal to 1 over F minus 1 over do, right? Do is given 10 meters. F, okay, radius is given 16. 16, so F is 8. Because F focal point equal to radius divided by 2. Right? But then here, the focal point, remember in convex, the focal point is always negative. Why? Okay, let's go to this one. the focal point is always negative. Why? Look, because the focal point here is always behind the mirror. That's why it's negative. Okay. Yes. Okay, so 1 over 1 over di equal to f is 8 minus 8, do is 10. You get here. Minus 18 over 80. Right? Minus 8 minus 10, then 8 times 10, 80. Minus 18 over 80. Minus is around minus 4.4. Okay. There's the location of the image. What about the magnification? M? The same? Okay, this one. The same formula? M equal to minus di over do. So minus di, just now we have minus 4.4. Do is 10. So plus then 0.44. Right. So magnification is 0.44. 0.44 means the image is smaller than the object. Just like our rear view mirror in our car, right? Okay. We go to the next one. Refraction. Just now it's all about reflection. Now refraction. What is refraction? Let me show you the. Okay, this is refraction. When one light coming from one medium to a different medium, right? This is reflected just now. We have. This is reflected, right? But there's also the one that we call refracted. Goes inside the medium. Light changes direction when crossing boundary from one medium to another. This is called refraction. The angle of outgoing ray mixed with the normal is called angle of refraction. Okay, just now, reflection this one, angle of this one equal to angle of reflection here. Right? Reflection or law of reflection. But for refraction, they have what they call Snell's law. Okay, depends on the medium. Yeah. So in this is an example. Yeah. You see the image there. A person's leg looks shorter when standing in a deep water, right? this leg here, this guy sees the leg of her is shorter. Why is it? The path of light traveling from the batter's foot to the observer eye bend at the water surface. Right? Because of different medium from air to water. So you only see half there. Okay? This is what we call reflection. Okay, this is the law of refraction. N is index of the medium. N, okay, this is N. Index of refraction of the medium. This is the formula of N. C. C is speed of light, right? Which is 3 times 10 to the power of 8 or 6. 8. Okay, meter per second. But don't worry, this one usually will be given in the question on the table. So this is the N for different material. In that index of refraction. Okay, so this is the formula. Okay, so we'll go through the question next week perhaps, or during the tutorial time. Okay, last one I want to discuss is on this one. Total internal reflection of a fiber optic. If light passes into medium with smaller index of refraction, the angle of refraction is larger. Okay. There's an angle of incidence for which the angle of refraction will be 90 degree. This is called critical angle. Okay, just now the formula, the original formula of Snell's law is this one, right? And 2 sine, for example. Okay. So if the refraction angle is 90, this one, it's 90 degree. Sine 90 is 1, right? Sine 90 is 1. So this one will be equal to 2. In the case of theta 2 here is 90, we call theta 1 is critical angle. C. So critical angle. That cause the refraction angle is 90. So this is the formula for total internal refraction. Okay. Okay, this is the case. So this is one medium, this is another medium, right? But then, if you look at the refraction, this is the incoming light, but the refraction is 90 degree here, goes here, 90 degree against the surface. This is one, right? Against this one, it's 90 degree. So this is what we call total internal refraction. It's all reflected. Okay. Totally internal reflected. So it's applied to this formula then. Okay. Okay, this is this example of the total internal reflection is binocular. Binocular often use total internal reflection. This gives true 100% reflection, which even the best mirror cannot do. It's all reflected, so there's no reflection then. Okay, this is in fiber optic. Depends on total internal reflection. They are therefore able to transmit signal with very small losses. This is incoming, for example, light, right? All reflected. There is no refraction. If there's refraction, there's a leak here. It goes here maybe, refraction. There's a leaking here, so it's all, there's one light goes out, which is refraction, refracted. But in here, it's all reflected. So this is what we call total internal reflection. All reflected, the light. There's no refraction. Okay, this is a cable, fiber optic cable. Okay, I guess that's it for today. By next week, we'll discuss the summary of all the chapter that we have discussed for your exam. So if you have any questions next week, just ask any questions for your exam. Maybe I will come up with some questions. Maybe previous exam perhaps. Let's see if I can find some. Okay, guys. Any questions so far before we stop? No, huh? Okay then. If you have no questions, then I'll see you next week. Stay safe and keep the spirit. Huh? Okay, guys. Thank you.
Thank you, sir.